So today we are going to talk about a discriminative method. It's called the logistic regression. We are going to spend 2 lectures on this topic. Now, logistic regression, as you can look at this diagram, we are sort of moving to the right-hand side of this linear discriminant analysis. So we spent a couple lectures on generative methods, especially the Gaussian model, and using the Bayesian decision rule. We sort of draw the connection from the generative model to the discriminative model last time. And now we are completely in this area of discriminative model. So there are 3 things we want to talk about. Logistic regression is the simplest one in a discriminative model. It has a lot of connections with the linear regression that we have seen, which we can tell from the name. It's logistic regression versus linear regression. So it's only the model that we're going to use in the regression setting. Then we are going to look at I think it's not deep neural network per se, but it's more towards the perceptron algorithm. Is a very baby version of the deep neural network. So if you can understand how a perceptron algorithm runs, then putting multiple perceptron together, then you can multi-layer perceptron, and then you put nonlinearity, you can get a deep neural network. So we will look at the very, very basic perceptron algorithm. Then we will also look at a thing called a support vector machine, which is very, very popular before the age of deep neural network. Okay. So here is the outline for today's lecture. We have 2 lectures on logistic regression. This is the first lecture. This lecture will be focusing more on the properties of this logistic regression. Next lecture will focus more on the computation aspects of logistic regression. So you will probably not be able to see any examples today, but you will see more examples next lecture. So what we want to do today is to motivate the discussion of logistic regression and try to compare the logistic regression with the linear regression that we used to see. In a particular problem, we want to ask, why do we want to choose this thing called the cross entropy loss, but not the L2 loss? Now, if you ever have any experience in deep neural network, you know that there's a thing called a cross entropy loss. It's one of the most popular loss functions that you can ever choose. So we want to understand the origin of this cross entropy loss. It actually comes from this logistic regression. And then we want to ask, why not use L2 loss? Okay, so there are some difficulties with the L2 loss. Then we will move on to interpret this logistic regression using multiple angles. Now, none of these angles will be perfect. Okay, so they're just giving you one way of looking at the same problem. So you'll be seeing this logistic regression from different views. Then we will analyze a thing called a convexity. Now you may ask, why do you want to talk about convexity in this setting? I want to show you that logistic regression, if you use the cross entropy loss, it's actually a convex problem, and therefore don't bother to use stochastic gradient descent. Even if you use the CVX program, you're guaranteed to get the true solution. Okay, so that can bypass some of the complications of not being able to implement your gradient descent properly, but you can still analyze the underlying property of this algorithm. Okay, so that's the outline. Now, let's start by looking at the linear regression. This is the linear regression model where you have 2 classes of data points, the yellow class, the blue class, and one is sitting at +1, one is sitting at -1. By linear regression, I mean that I want to find an orange line that cuts through all these data points such that the error is minimized. And by error, I mean that the distance from the blue point to the orange line. And this distance has to be the vertical distance. Okay, so it has to be the perpendicular distance from the data point to your line. Okay, and so you want to minimize the sum of all the square differences between the point and the line. And if you can solve that equation, that minimization problem, you will be able to find a W and also a W0, where W defines the slope of this line, W0 defines the y-intercept of this line. And once you have found this orange line, you set a simple threshold. In this case, because the 2 classes, they are -1 and +1, the threshold is 0. And once you put a threshold here, you get a classifier. And the classifier we call them hypothesis functions. Okay, this hypothesis function will be a step case function, and after this point, you will get you will say that all these labels are predicted as +1. Before that, it will be predicted as -1. So this is a linear regression model, and then we try to build the connections with the Bayesian decision rules, in particular the Gaussian case, and we show that under certain conditions they're the same, but under other conditions they're not the same. So this is the linear model. Now, one question you ask is that in the linear model, this kind of fitting doesn't really look good, right? You're trying to use a straight line, and then you try to fit the data points, and then clearly the data points, they don't lie on the straight lines. Of course, you can always fit a straight line through all these data points, but then the straight line that you're getting doesn't seem to have too much geometric meaning with respect to the data points that they are appearing in this plot. So a natural question then you ask is, can we find a function that will fit better to all these data points? And you also want to keep some kind of continuity, in a sense that you don't want to have a sharp cutoff function, and then because for those functions it's not differentiable, you cannot take the derivative, it's just making your life a lot harder. And so you ask, can I find a continuous function that can somehow follow the pattern of these data points? And if I can do that, perhaps this red line can be my discriminant function. And I can also set a threshold above which I will call it +1, below which I call it -1 or 0. And in this particular problem, you can choose the discriminant function to be like this. Okay, it takes a very special form, which we will look at it very carefully. It has this 1 over 1 plus e to the power minus w transpose x plus w0. It's taking this form. Now, because of this transient property of the curve, then one thing that you realize is that compared to the hard threshold, okay, hard cutoff, this is sort of like a soft cutoff version of the hard cutoff. So perhaps we can, instead of modeling the decision as a sign on the discriminant function, maybe we can just directly use this function as my discriminant function. Okay, instead of putting another sign, I just use this function itself directly. Okay, and this function is called a logistic function. So what we are going to do is that we are going to look at the data points, we are going to look at this function, and then we are going to look at a way to fit all these data points using this logistic function and see how well we can do, and then we want to analyze some of the theoretical properties. So the function that we are using takes this form, is 1 over 1 plus e minus gx, where g is your discriminant function. And so you can compare to the previous case where hx is the sign of w transpose x plus w0. And now, instead of using a sign function, you use this 1 over 1 plus e to the power minus g. Okay, so this function, you can call it a sigmoid function. You can also call it a logistic function, depending on which one you prefer. You plug in the g as this w transpose x plus w0. That will give you the sigmoid function, evaluated at x. The 1D form of this function takes this expression. All right, so it's 1 over 1 plus e to the power minus a times x minus x naught. Okay, so you reduce this high-dimensional vector to a 1D problem. And if you do that, then this w transpose x plus w0 in high dimension, when you translate to 1D, then it will take this form. So we can look at this form and see what it means, okay? So there are two parameters in this logistic function. One is the parameter a, the other one is the parameter x0. They have different meanings. First of all, this x0 defines the transition point of your function. This is a logistic function. It's a sigmoid function, so it has to have a transient location. The transient happens at x0. The A will define the transient speed. If you have a very, very big A, then you will have a sharp transient. If you have a small a, then the transient will be slow. Now you can try to ask, well, how can these be possible? Now let's look at this equation, x0, okay? So you can imagine that I fix a, and then I sweep my x from minus infinity to plus infinity. So when x is very, very small relative to x0, then what do you have? You have 1 over 1 plus x e to the power what? E to the power a positive number. Okay, and so this guy will go to very, very big number. So you have 1 over infinity, and therefore you go to 0. As x is way, way, way bigger than x0, then you have e to the power minus a big number. And so that will go to 0, and so 1 over 1, that will go to 1. You see that? Okay, so at the two extreme cases where x is minus infinity or plus infinity, you can see that the sigma function will go to 0 or 1. And then the transient happens at x equals to x0, because when x equals to x0, then you can show that the slope is maximized. Okay, something that we can do later, okay? And when x is equal to x0, then this expression is just given by 1 over 1, right? 1 over 2, okay? Because if you set x equals to x0, then here you get 0, so you have 1 plus 1, so you have 1 half. Okay, so this point corresponds to 1 half. Now, the role of this a is that it changes the slope, because if you make a big, then for the small perturbation of x, then you're going to see the transient very, very rapidly. Okay, so that's why for the large a, you have this curve, for the small a, you have this curve. So the meaning of this logistic regression, you can see that these two parameters, they sort of define where do you want to set the cutoff? Where is the decision boundary? In the 1D case, of course, the data, they are distributed on a real line. So they're either on the left-hand side or on the right-hand side. So you want to say, where should I set the cutoff? And how rapid should my cutoff be, right? So that would define the decision boundary. Okay, so this slide is just a summary of what we have discussed. Okay, so when x goes to plus infinity, then h goes to 1. When x goes to minus infinity, then h goes to 0. And then that is the curve. If you can recall your probability course, you realize that this function is monotonically increasing. The lowest point is 0, and then the highest point is plus 1. It has a lot of similarity to do with a probability, because if you look at the cumulative distribution function, then you see that the function is monotonically increasing as well. The least point is 0, the maximum point is 1. So this function, you can treat it as like a probability distribution. It has a very, very interesting relationship over there. Okay, you can try to calculate the derivative of this function, and calculating the derivative is a little bit tedious, but it's not too hard. So what you can do is that in the 1D case, you can take the derivative with respect to your x, and then you look at this expression. Now, this is 1 over 1 plus e to the power something, and so you have minus 2 as the power coming out, and then by chain rule, you have this exponential term and then minus a. Then you start to group the terms. Now, if you trust my calculation, assuming there's no bug with my calculation, you go all the way to the bottom, to this line. Okay, now of course you need to go home and verify my calculations. You go to the bottom at this line, you realize a very, very interesting expression, that the derivative of this logistic regression is a times 1 minus h times h. Now what is h? H is just this expression. Okay, so you can see that when you take the derivative of your h, is actually giving you back your h in some very, very unexpected form. Okay, now this h, you can look at this. This is 1 minus h, and then this is h. If you treat h as a probability, this is like a variance type of thing, right? So think about a Bernoulli case, Bernoulli random variable, and imagine that h is your probability of getting a head or a tail. Then h times 1 minus h, what is it? This is the variance of that Bernoulli random variable. So it has some connection to the probability as far as we can tell from now. Another very interesting property is that since your h, I just showed you that h is monotonically increasing, its maximum value is 1, the minimum value is 0,
And therefore, for any x, your h is bounded between 0 and 1. Okay? And since it's bounded between 0 and 1, then your 1 minus h is also bounded between 0 and 1. And therefore, this quantity, 1 minus h times h, is also bounded between 0 and 1. Correct? Okay? And if this is bounded between 0 and 1, then you know that this is a positive number. This is always bigger than 0. Right? And therefore, you can sort of show that the function, the logistic function is increasing for any positive choice of A. Okay? So for any A is increasing. So it's an increasing function, and therefore, you can view this H as a CDF, cumulative distribution function in the probability setting. A pictorial illustration of the logistic regression can be shown as follows. This is a picture I downloaded from the internet, from this link. Let's say you have two sets of data, the red data points and then the blue data points. And what I want to do is that I want to find a separating hyperplane that classify them into two classes. From the Bayesian approach, what you are going to do is that you are going to put two Gaussians, and then from the Gaussian, you're going to draw a line. The logistic regression is trying to fit the data immediately using the function that I've just described. The function that I described is a 1D function, but you can easily extrapolate this idea to high-dimensional functions. So in this case, it will be a two-dimensional logistic function. So you are trying to fit this data points using a function like this. Okay, it's a logistic function in 2D, so you have a staircase type of behavior. So the slope of this staircase function is determined by your W, because the W vector defines the slope of your logistic regression, right? And also the x-intercept, where do you want to cut, that is your x0. So you can move this step case function to this distribution, and then you move around, and then you find what is the best logistic function that can fit the data point. Now, if you can do that, then you can see from this diagram that you can draw a lot of these lines that we call the contour lines. Okay, so the contour lines, they say that what is the probability that my data point should belong to this class according to my logistic predictor. That will give you some value. And you can see that this logistic regression, because of a very, very sharp slope here, usually, then you kind of separate the two classes into two, and then the transition is sharp. Okay. Now, of course, if you choose a very, very slow transient, then you can make this transition bigger. But normally, what we have been observing is that usually you make the transition really, really sharp, so you can have the two classes. Okay, so that creates some little difference between a linear regression model and also the logistic regression model. In the linear regression model, before you take the sign function, okay, before you take the cutoff, before you take the threshold, the contour, they're kind of linear, right? So even if you go to these locations, you're not absolutely certain whether it belongs to class 1 or class 2. You only say that, okay, according to my linear regression model is higher value or lower value. But in the logistic case, you have a very confident way of saying that, oh, okay, this belongs to class 0, this belongs to class 1. That comes from the natural definition of the logistic regression, because by construction, it is a 0-1 function. And that's why in the linear case, in the linear regression case, you have a straight line, but in the logistic regression case, you have a stepwise function. That causes the difference between the two. Now, you may ask, okay, what is the ultimate performance on testing cases? We'll come back to this point later, next lecture, and I'm going to show you some situations that logistic regression performs better than linear, and sometimes linear performs better than logistic, and I will tell you what are the pros and cons of choosing which model. But before that, let's spend some time looking at different perspectives of this logistic regression. Okay, so so let's skip this slide. Okay, let's go to here. So let's look at the loss function of the linear regression again, and then we are going to make a contrast between the linear regression and also the logistic regression. So the linear regression loss function takes this form. You have a sum of all the individual losses, and we have gone through these equations before. It would be a 2-norm square expression. So we can skip that. Now, the training loss function of the logistic regression is given by this. Okay, so you may try to look at the difference between these two. Here, in the logistic case, the loss function also takes the form of a sum of individual losses, which is the same as here. Okay, that 1 over n doesn't really matter. Okay, now, so in terms of this expression, they're the same. However, you realize that in the logistic regression, I'm putting the hypothesis function h. And in the linear regression, I put a g. G is a discriminative function. The reason I'm putting in here is that for logistic regression, I'm literally putting the step case function. There's nothing called the discriminative function anymore. Okay, so there's just the hypothesis function. So that's one difference. And then the second difference is this individual loss. The individual loss of the logistic regression takes the form of the yn sample. So this is your label of the y entry. Xn is your input data. Okay, so input and output pair. And then you put into this form of y times log of your whatever you have predicted. Now, this prediction is actually what? It's actually close to 1 or close to 0 because of this choice of the hypothesis function. Same for here. This is 1 minus your decision, and then this is 1 minus the true label. And of course, you have a log here. This is obviously different from the square loss function that we used to see in the linear regression case. Okay. Now you may wonder, why do I want to choose this function and not that function? I would discuss that. But I want to spend maybe another 1 minute or 2 to explain the meaning of this expression before we address the difference between the logistic and also the linear regression. This function is called the cross entropy loss. Is also widely used in the deep neural networks today. Okay, whenever you have 2 classes, or even multi-classes, you want to do a classification. When you try to train a deep neural network, the loss function that you would typically see will be this cross entropy loss function. In this case, it's a 2-class cross entropy loss function. So we can look at the cases by putting in certain values of h and y. Okay. Now let me remind you, h is the hypothesis function is going to give you either 0 or 1. Okay. Y is the true label, is going to give you 0 or 1. Okay. Now, of course, we can debate that h is a soft threshold, so you may have a 0.5, 0.8. But let's imagine that the transition is fairly small. Okay. All right. So now imagine that we are in this case where the true label is 1. Okay. Yn is 1, and then the predicted label is also 1. Okay. Let's look at this case. Then you compute yn times log of h. Okay, so you can do the log of h, log of 1, that is 0, times yn. Okay, yn is 1, but since log of h is 0, then you get 0. Okay, so that means if you have a correct prediction where your h matches with your y, your loss is 0. Okay, how about the other term? It doesn't matter because you have 1 minus 1 here, and then 1 minus 1 here. Okay, so that will be gone. Okay, now, how about another correct case where h is 0, when your y is also 0, then these two will multiply together to give you a 0. If you have a wrong prediction where h is 0, your y is 1, then this one will go to minus infinity, and you have a 1 here, so you have minus infinity. When this minus infinity go to your summation, you have a minus sign here. That will give you plus infinity, and therefore your loss will explode. Okay, so as long as you have a wrong prediction, this loss will be big. Okay, as long as your prediction is correct, your loss will be small. So you're trying to find what? You're trying to find a theta. Theta is your model parameter, meaning that your W, your way, your slope, and also your y-intercept. You're trying to find a good theta or your W's such that all these cases, they are correct. Okay. Now you may ask, okay, what if I have one single case that is wrong? Then that has to go with how sharp your slope has to be. If your slope is really, really, really sharp, then one mistake is going to kill you. Okay? But if you have a mistake there, then you may want to reduce your slope so that you become softer in terms of making that decision, so that your loss will be lower. Another way that you can handle this is to use a regularization, because cross entropy, you can show that it has some problem that is convex, but it's not strictly convex, and so you can have a lot of global minimizers. Okay, and so you can put a regularization to get a better solution. But in any case, this loss function seems to make sense. Okay, compared to the linear regression, this expression also makes sense because you only have two classes. If it's correct, you want it to be zero loss. If it's wrong, you want it to have a very large loss. The linear regression is easier to deal with because it's square. You can take derivative, but it doesn't seem to capture the 0-1 binary behavior of the thing that we want in a classification setting. Okay, so that's the logistic regression. So now we can ask a question: why not use L2 loss? It turns out that you're welcome to put the logistic function into this L2 loss, and then you're welcome to minimize this function. It's just that this function is not easy to minimize. Let me explain why. You put this logistic regression in the 1D case, you put this equation into this square term. You show that this J function, you look at this J function, you can prove that it's actually not convex. Okay? And how about this logistic loss? This logistic loss is complicated in theta, however, it's actually convex in theta. And therefore, by solving this problem, you're not guaranteed to get a global minimum. But for this one, you have a lot easier problem to work on because that will give you global minimum. All right. So here is experiments of your loss function. So I'm setting x equals to 1, y equals to 1, and I'm plotting your loss function as a function of theta. And this is the L2 loss function. This is the logistic loss function. Okay, and so you can see that this L2 loss function is concave for all the values before 0, and then it's convex after that. Okay, so it's a concave convex function. And for this one, you have a concave function. Okay. All right. So okay. So by the way, concave means negative convex. Okay. So if you do gradient descent, you might be able to track a local minima. Okay. This 1D case may not be the case. However, for high dimensional problems, you will see a lot of trouble in using the L2 loss.